Good morning, good afternoon, everyone, and welcome to another ARA Webinar Wednesday. I'm Jerry DiMaggio. I'll be serving as your moderator for today's program entitled Predictive Modeling for Dredging Needs. Now, it's my pleasure to introduce my colleague, Hans Jacob Broder. Jacob has a background in physics and mechanical engineering with a focus on physics-based simulations. During his 3-year period with ARA, he's transitioned into a role as a data scientist and focused on building predictive models to help us understand real-world phenomena. Jacob completed his Master's of Applied Data Science from Syracuse University and has a strong understanding of the tools relevant to creative, informative predictions and presenting strong visuals to help us understand the information provided. Next slide, please. I'd like to turn the program now over to Jacob.
Hi, everybody. I'm Jacob Broders, and to get us started, I have this map of the US with each bin showing the number of surveys that has been done in the waterways of that location. This is to give some understanding to why we chose to focus on Southwest Pass for our model building. You can see that it has over 17,000 surveys done, whereas the other bins locations around the US are usually capping off in the hundreds, with a couple coming up to the thousands, but the 17,000 is definitely by far the highest. And because of that, it gives us the largest amount of data to work with to make our predictions, and then hopefully these predictions can be generalized to other regions of the US. So to go into why we focused on Southwest Pass, it has a lot of cargo coming through for both trade and transport, over 250 million tons. And each year, because of all of the waterways that feed into the Mississippi River, there's over 25 million cubic yards that have to be dredged each year, which is a very large amount. And right now, our dredging predictions lead to only a 14-day lead time, and that leads to mobilization challenges with the dredges. And when the dredging isn't done proactively and you have to do emergency response dredging, you lead to a draft restriction where there's too much sediment buildup for these vessels to have the clearance they need to make it up the river. And we're having on average 90 days of draft restriction. When it's drafted, you're not getting any trade. It slows down supply chain, and it can also slow down just moving anything to where it needs to be, including people. And then because of these delays, we're losing hundreds of $millions on these short-term dredging contracts. A lot of it comes down to the fact that emergency dredging, of course, is going to charge higher contract prices than the proactive dredging that we hope to do. And then in Southwest Pass, we also need to continuously survey all of the riverbed to see if we need to do any dredging to remove this sediment buildup. Right now, these surveys are done daily with depth sensors on the bottom of the vessels to always have up-to-date information. But it's not surveying the entirety of the river. It's surveying locations that are being traveled by these survey vessels. Southwest Pass, which is what we're focusing on, is made up of 13 reaches. You can think of a reach as just a straight section of a river or waterway. It goes back to essentially an area that you can sail without having to make a turn. All of these conditions, the unpredictability of the river, conditions in the Gulf of Mexico, make it very hard to make an analytical model, almost impossible, for how the sediment accumulation happens over time. So to predict these changes, we're hoping to use machine learning models to find what the right input variables are and to find some nonlinear similarities that are going to arise from this. So our goals to improve the current state of practice. We want to increase this lead time from 14 days to 45 days or even greater. The larger lead time you have, the more you can focus on getting dredges to where they need to be at the right time and not have to overwork these dredges or lead to emergency contracts. We want to know where the dredging needs to be done. So even with the continuous surveying, sometimes there's a lot of buildup that happens quickly in one region and maybe not the entirety of the river. So knowing what these trends are, we can know where these dredges need to be sent in that 45-day window. And also knowing the amount that needs to be dredged. So if you send a dredge to a region, but it doesn't have the capacity to handle anything, this contract that might only want to take 2 to 3 days could be extended for up to a week because it's going to have to keep on making trips to get rid of all the sediment that it has dredged up. So what we're looking at are these 13 channel frameworks, these 13 reaches that make up Southwest Pass. We're using 11 years of historical data. And since it's not all perfect data, there is missing data for some of these areas, we're using interpolation to kind of fill in these missing gaps. So to summarize the problem, sediment is deposited in the riverbed, creating an unnavigable section of the river. When the river is unnavigable and unpredictable, it halts necessary trade and transport. This late notice of dredging results in high-cost emergency contract, and a solution with a larger time horizon would reduce delays in trade cost and of the cost of dredging. We have so far made 3 models. We call Model 1, well, we have Model 1, which is a singular prediction, and then we have Model 2A and 2B, which is more spatial predictions. It uses map data to get this information. Model 1 is just to predict a shoaling trend, and it uses it makes a time series prediction using an LSTM, which is a type of model I'll be talking about, to get daily volumes, and then it classifies these shoaling trends as an increase or decrease. In our case, a steady shoaling trend is also considered a decrease, just because the two classes are, do we need to dredge or do we not need to dredge? And in the case of no shoaling, that would also be a no need to dredge case. Model 2A tries to find what percent of the channel area has a depth shallower than the threshold, which is a maintained depth, which changes from reach to reach, but in Southwest Pass that we're looking at, it is a constant 50 feet as of now. This uses a CNN, which is a convolutional neural network, to do time series forecasting, which is also a regression model. Our third class, Model 2B, is also a CNN, but it does image classification instead of a regression using these images. And it's trying to predict, is dredging going to be needed 6 weeks from now? It's just a yes or no answer. You don't have an output of amounts dredged, overall trends or things like that, just a yes or no based off of historical times when dredging has happened before. We're hoping in the future to move to being able to use an ensemble framework, which would combine all of these models, which would get the best results from all 3, allowing us to not make only stronger predictions, but to predict on a wider range of outputs, and would allow our LSTM to be able to use spatial data and our CNN to be able to use more data from upstream reaches and variables like that. So Model 1 is the LSTM. The first picture that you can see here is what an LSTM cell looks like. The thing the LSTM cell has is it has something called a forget gate. I'll talk about that a little bit more when I get into the model. And then this shows that the LSTM can predict multiple outputs simultaneously, which you see right here, that we're making a full 45-day prediction, not just one prediction 45 days down the line. This is our overview for Model 1. I'll be doing one of these for each model. So our variable predict is our shoaling trend, which is based on the volume of shoaling. Positive shoaling trends, we need to dredge. Negative or neutral shoaling trends, no need to dredge. Our scope here for what we're trying to predict is all of the shoaling that occurs in the 35 miles of Southwest Pass, all 13 reaches combined. It's a very, very large prediction area. And because of that, we don't really have a lot of spatial accuracy. But what we can do is say, yes, we need to dredge, and based off of the surveys that are being done daily, they will know where they need to send the dredges. Our input data is data from CSAT, of the shoaling volumes, and then also gauges from upriver, from river gauges and USGS. We're looking at variables like stage, turbidity, discharge, precipitation. So we combine all of, like I said, all of the volume from all 13 reaches to make a single point prediction. And we get daily values for each of these, so you have a lot of input data from those 11 years. The method is the LSTM regression, which we then move into a classification of the yes or no. This is currently fully developed and is being migrated to the cloud so that people can use this model to say when they need to dredge, if they need to dredge. Down here, you can see the steps that go into getting our final model. You start off with a data ingestion and preparation. You then move to a feature selection submodel, which is choosing what of the variables that we've aggregated are good to predict on this time series. As times of year change, conditions upstream change, this will also change, which are the best variables to use. We then go to the forecasting and regression, which we started with an MLP, but we've moved to an LSTM. This then gives us our forecast of our 45 days. With the 45-day forecast, we then go into a classification of yes or no on the dredging, and final a model evaluation to see, is this model performing better than what we had before? Not just better than what is the current state of practice, but better than our previous models that we've worked on. So to talk about data collection, the data is collected from 69 stations along the Mississippi and its tributaries. These locations range from Southwest Pass all the way up to St. Louis, Missouri. As you go further and further upriver, you're going to expect less and less effects on downstream, but we like to kind of collect data all along the way because sometimes that data can be very useful. Also, not all stations have all variable gauges. Turbidity, for example. Turbidity is how many dissolved solids are in water, which is very useful for us because these dissolved solids are what falls out of solution and becomes the sediment that we are then hoping to dredge. The other things we look at are stage, just how high the river is, the flow rate, how quickly it's moving downstream, the temperature of the water, and the time of year. The time of year is important because you will see things like in the spring, when ice is melting, snow is melting, you're going to expect a lot more water to start coming down. So knowing that this increased flow rate is because of a change in the time of year and not because of some event that has happened unpredictably upstream helps the model to know why this data is changing. After we collect this data from these stations, we look through it, and if more than 10% of this data is missing, we remove it from the data set and we don't use that variable anymore. We then interpolate the missing values for anything that is less than 10% missing. We use a 7-day rolling average on all of the data to remove any of the spiky rigidness that you're going to see from taking daily samples, to try to find what you see as the overall trend in that weekly window. Our output value of the shoaling accumulation is always going to be used as one of the inputs for the model. So you're always predicting on one of your variables instead of just predicting from the upstream data to make a prediction on a variable that it's not fully trained on. We tried using other CSAT data, sediment in other reaches higher upstream, but this was found not to add any value to the model. When we did that, the model continuously just selected the data from Southwest Pass over and over again to look at, because of course the data that it's predicting on is going to have the highest correlation with the data that it's trying to read. This was not great because we were using all of the individual reaches as inputs, and this led to a lot of data that was being shown in multiple ways. If you show both the entirety of Southwest Pass shoaling accumulation and, for example, Reach 6's shoaling accumulation, those are going to have very, very high correlation, but it's not actually adding any more information to the model to learn on. What we have next is our feature selection. I was talking about this when we were talking about the variables that we're going to use for the model. In a world where we have infinite computing power, you'd put in every single variable, you'd get a very, very strong prediction. But as you're adding more and more data to predict on, it's going to increase the time that it takes for the model to run, up to a point where it's not really useful. It's taking so long to run and so long to train that by the time you're done training it, you have more data to start training on it again, and you never get to the point of making real predictions. What we ended up looking at was XGBoost and principal component analysis. So XGBoost makes these decision trees, and it chooses one variable or another. And as it goes down, it keeps on selecting more and more variables at each one of these splits in the tree. And then it ends up on a final variable that has the strongest correlation with our variable to predict on a set of what we selected to be 7 variables. PCA is a different approach where you create, it's going to get, I don't know how to explain this in a not extremely technical way, so pardon me. It creates orthogonal vectors of the data you're looking at, and it tries to find fully different principal components. Basically, the data that is least aligned with each other, but is still able to make predictions on the variable that you're trying to predict at the end. You can see here it's chosen that these 2 principal components in this simple model for feature 1 and 2 are offset from each other by about 90 degrees, but offset from the x-axis by about 45 degrees. This is to show what both models gave us as the feature that it's selected. So you see here on XGBoost, it's selecting a very, very wide range of models, wide range of variables for each of the different time series that we're looking at. These time series are separated by about a little bit over 3 months. So in our 11 years, we have many, many of these to look at. So then we can see the feature importance for each one of these on average. Week of year, like I said, is a very important one because seasonal trends for the river are very, very important. But you can see certain things like here, red rock stage selected often, not always. And then sometimes things like the Southwest Pass stage at mile 75, not selected very often, but every once in a while, it would have very strong correlation with the shoaling that had occurred. So we've chose XGBoost because comparing it to PCA is just selecting the same variables over and over again. And not only is it selecting the same variables over and over again, its performance on the model overall, when all other variables were kept static, was also weaker. So for forecasting, we chose 3 different models that were tested. We chose a random forest, which is a tree searching model. So kind of looking at the variables and saying, okay, if this is over 5, we go to the left branch of the tree. If this is under 5, we go to the right branch of the tree. And you work your way down to predicting a number at the end of all of these branches. Multi-layer perceptron, which works very similar to an LSTM. It's just missing that forget gate. And then finally, the LSTM. We found that the LSTM was by far, after some changes have been made, one of our strongest models. And then we compared, by comparing this against the 45-day output and using a normalized root mean square. So kind of how strong are its outliers is what a normalized root mean square is good for finding. And we care a lot about the outliers in this because the outliers are when we're going to want to dredge. We ended up going with a 60-day prediction because it did perform better. Okay. Now, I know you've probably heard me say LSTM now a lot. Let me describe what an LSTM is. It stands for long short-term memory, and it doesn't have a problem recalling old data compared to an RNN. RNNs, as the data gets longer and longer, the further back the data is, the less important it is, which is not always the case for us. Sometimes the events from 60, 40, 80 days ago were the most important events for what's going to be happening at Southwest Pass after that time period. So that was one of the strengths of the LSTM. The other thing that the LSTM has is something called a forget gate. It has the ability to forget data. So a good way to think about this is I water my lawn twice a week, right? If it rained, I don't need to water my lawn. The model can't realize, well, if it rains, you don't water your lawn. But if it picks up a trend of, well, whenever it rains, you're not going to water your lawn, it forgets to water its lawn. Is a way that I like to think about how this forget gate is working. Using this, we then started to make some forecasts. These early results look promising, but we still did have large errors in some extreme cases. You can see on the right, we have these two different predictions. When there's only a slight change from the forecast start to forecast end, it's a little bit higher, but you can see that it's fairly close. Not even a whole 100,000 cubic yards off, which sounds like a lot, but in our case is fine. Whereas on the second prediction, when it's climbing greatly, it never really wants to make these massive predictions. Because if it's making massive predictions, it's going to usually perform very poorly. What we decided then is by looking at this, maybe we're not looking at a true regression problem. We're looking at a classification problem. Yes, the regression is an important way to figure out what our trends are, what we're looking at, and where we're going. But knowing if we need to dredge or if we don't need to dredge is actually more based off of, is the direction correct? Is it growing? Is it decreasing? So while this would have been considered a good model before, and it still is considered a good model after classification, this is also a good prediction after classification because it got the trend correct. And with the constant surveying that's happening, they will know where to dredge and hopefully also know how much to dredge. So for a first attempt at this was a strong prediction. So to go back to that a little bit, talking about forecasting, we had to determine what a minimum slope was. Is an increase of 10,000 cubic yards a day a need to dredge? Well, after some threshold, it's going to be. But that's where the daily surveying is going to come into effect, right? You're going to get these surveys every single day. You're going to say, we're getting close to the line of where we see that we need to dredge. Let's dredge, 2 weeks, 3 weeks from now. Whereas a very, very large increase is going to catch them by surprise, and they're going to want some predictive model to know that they need to dredge. So accuracy, in this case, very important. We want to be right as often as we can. But what's actually more important than that is this other variable called recall. How often is it saying we don't need to dredge when we do? So our model was trying to get accuracy as high as possible and recall as high as possible. And the way to get recall high is to lower this value here. So in our case, a real value of 1 is yes, dredge, and a real value of 0 is don't dredge. Our don't dredge case, when we're not supposed to dredge, very, very strong. This is not how many times it got it correct. This is just the total makeup of the predictions. And then we also have a lot of cases as well where it says, oh, you need to dredge, but there's no need to dredge. And while signing contracts to say, okay, go dredge the river when you don't need to dredge is definitely not the best solution, it's a whole lot better than the solution of saying there's no need to dredge when there is. Because when we don't dredge and we do need to, it's going to lead to a draft restriction. It's going to lead to supply chain issues. Everything's going to slow down. So we want to minimize false negatives is really what we're hoping to do here. So looking at different slope values, we found that a slope value of 200,000 cubic yards a day gave us our strongest results. On the right, you can see our legend where this dark red is a false negative. This salmon color is a false positive. The dark green is a true negative. And this kind of lighter green is a true positive. And based off of our metrics from before, with recall and accuracy being the things we care the most about, this second case was what we found to be the strongest. So a little summary of this model. The results are a great step forward from the current state of predictions. We're achieving a 76% accuracy and a 71% recall. So 71% of the times when there is a need to dredge, we're catching it. Obviously, we want that number to be higher, but I think we're all very happy with this for our first attempt at this model, and happy enough to actually move it to the cloud to use it as a real predictive tool. Of course, it's not ready to be the only tool yet, but it's definitely promising. And this model also showed that machine learning methods work very well on predicting shoaling rates and when we need to dredge compared to the current practice, which was not a 50-50, but was not a very strong method. You're going off of one gauge reading and just historical data. Whereas our model is taking many, many gauge readings and it's finding the connections between these readings upstream and what's happening downstream. So let's move on to our next model. This is model 2A. This is the convolutional neural network that is doing regression compared to model 2B, which is the convolutional neural network, which is doing classification. So this is what our input data looks like for this model. It's just what is the depth below datum, or just depth below the river that the riverbed is at different locations based off of shoaling and just natural geography. We then feed it into this, which is a visualization of a convolutional neural network to get an output over here. These green and blue dots are don't dredge predictions, and the red and yellow dots are do dredge predictions. Yellow is before a deepening happened back in 2020, where we moved the depth of the river from 48.5 feet to the current 50 feet. Similar for the green dots being the don't dredge in that case previously. Looking at the image really quickly, what we care a lot about this is not we're not caring about the locations of these dots. We really are worried about how close they are to this x equals y line that you see cutting through the plot. So our overview for model 2A. So our variable predict is the percent of the channel with an area shallower than our maintained depth, meaning if we have it at 50 feet, it comes at 49 feet, or comes up at anywhere between 49 and 0 feet, that's going to put a checkbox as this is below. This is below where we want to maintain. For this, we start off with a smaller scale. We only looked at reach 6. Remember, those reaches are just the sections of Southwest Pass, broken up into 13. Our input data is just these CSAT daily derived depths. So while those were also used in the previous model, we're now using these geographically instead of just accumulating all of the numbers into their sum. Our spatial segregation is the 10-foot by 10-foot grid, which we get from CSAT using their hex bins, which are just how they accumulate shoaling throughout each reach. This is using daily data, and then our method is a convolutional neural network supervised regression, and our status still under development, but we do have some strong results for this one so far. So the first step is our data preparation. We want to look at an image like this and get back how much of this is below the threshold that we're given. Doing that across all of the data we took from Reach 6, we ended up with this histogram, where you see the majority of it, only 5% is below, and then it almost completely drops off after 20%. We chose 20% to be our threshold in this case. We're looking into numbers, but right now 20% is what we've been working with. These floor maps that you're seeing here are then converted into arrays of just depths readable by a convolutional neural network, and then we're creating a separate value, which is after 6 weeks, what is the percent below threshold? Like I said earlier, the deepening occurred in 2020, so the depth for this threshold is based at the time of the survey, not based off of the modern 50 feet. After we do this, we move to an image masking and normalization. So these images are normalized between values of 20 and 80, with 20 being the minimum depth and 80 being the max depth. We didn't go down to 0. By going down to 0, it caused issues with what we're going to talk about next, which is masking, because we're using a 0 mask. So it wouldn't be able to tell apart what isn't part of the river and what are the low parts of the river if we were to go down to 0. So to talk about image masking. So this is a good example of image masking. you have this image, guy on his horse with his dog, and then using a mask, we're able to cut out just the horse. In our case, we're trying to cut out just the river. The location, all the area around the river, we set that to 0, almost telling the network, do not look at this value. This value is not important. We tried random masking. Random masking, while an approach in some problems, in this where we have such a static region that we don't want to look at, the 0 masking performed better. So let's talk about what a convolutional neural network is. So a convolutional neural network uses these things called filters. Filters, think of them as just a grid square. And these grid squares look at one section of the image at a time. This, in the bottom left, is a convolutional kernel, one of these filters I was talking about, to find edges. So it takes this picture of an animal, and it puts this filter over it, and it can find the outline of the animal. You lose color data, you lose some of the detail, but we're able to find the edges. You can see a clearly outlined ear, the eyes, and then the overall face. Another thing we used here is called max pooling. And max pooling is a way to decrease the size of the image you're working with so that you can work with more convolutional layers simultaneously without running into memory issues. Max pooling, very simple concept. You choose a grid size. In this example, it's a 2x2. You look at each 2x2 grid, and you say, what's the highest number in there? Okay, that's the new number for the reduced image. The way that these networks work is you stack a lot of these convolutional layers and a lot of these pooling layers together to be able to give yourself an output at the end. So more on the convolutional neural network. On the left, you see a picture on the car. On the right, you see a prediction that says car. Simple way to think about it is that we look at that and we say that's a car. The way the computer is going to look at it is it's going to run all these convolutional filters over the car, getting things like its edges, its curves. These filters are supposed to extract features. As time goes on, these features get a little bit less readable to humans, but it is how the computer reads them. And it looks at this final output that you see here, and it somehow looks at these images and says, that's definitely a car. So our model takes 8 weeks of input data and stacks them together. You can think of this stacking similar to how images work, JPEG images, for example, where you have 3 color channels, red, green, blue. But instead of stacking colors, we're stacking temporal data. So this is a way of tricking the CNN a little bit into treating time series data as image data. So CNNs, really strong with spatial data. RNNs, like the LSTM and the MLP-B4, are really strong on temporal data. But by doing this stacking, we've made the CNN able to analyze both. The overall structure of the CNN, we put in these 8 stacked images, put them through a bunch of layers, and at the end, we convert it to a string of digits and get an output, and then that output says 10% is below the threshold. Simple way to think about it. So by stacking it, we're able to get more data and kind of compact each day that we're analyzing into a group of values. These values then, like I said, fed through a 1D array, which is similar to the RNNs from before. And that's how we're getting the value of the CNNs and the RNNs simultaneously. Now on to our predictions. So predictions are made on a randomized test of dates. We didn't want to just train it on the pre-deepening trends and then test it on the post-deepening trends. That would probably lead to some very, very poor results. But we can see here that besides this first value, which is definitely off by a good amount, that we're getting our predictions, which are in orange, versus our actual values that are in Y. Things like 5% is what the actual value is for the amount below the threshold, the percent below the threshold, and we're predicting 4.7. And that kind of, you see that trend continue through most of these. This gave us a mean average error of 0.017 and a root mean square error of 0.025. The mean average error tells us overall how well did we do on predicting the data, while the root mean square error looks at the outliers. So this value being a little bit higher means that we do have some outliers, as you can see down here and up here. But both of these values being well below 1 are very strong results. Just to, if you need to look at this a little bit more closely, the one trend I want to improve here is that we're usually under predicting the actual. There's a few cases where we're over it, but it's usually under. So with some model tuning and things, adding more layers, model tuning, maybe changing the input parameters a little bit, we might be able to get them closer to accurate. Or, like I was saying earlier, where we care more about times we do need to dredge, the times we don't need to dredge, predicting a little bit above would actually be fine as well. And then you can see this here as well for these predictions. It's not quite to the point where you could cluster it into two distinct groups. Obviously, these could be clustered well. But you do see a separation between our predictions above and below our threshold of 0.2. So our model did give strong results when using 0.2. And these values were chosen by us as a test case, but the Coastal Hydraulics Lab over at ERDIC, part of the Army Corps of Engineers, has asked us to investigate these historical dredging for future model and testing to get an exact value for them. Our future work on this, scale it up. Like I said, we only worked with one reach. Next step, we're combining 3 reaches together. And as time goes on, we're going to work our way up to all 13 reaches, hopefully. And we'll be able to get models for all 13. So you start off with an overall model for 13 to see, okay, does dredging need to happen in Southwest Pass? Okay, let's tune into one of the reaches individually. Is this where we need to dredge, or is this where we need to dredge, instead of just looking at the entire body as a whole? So, in summary, the first test of using CNM for predicting dredging needs shows promise. Definitely want to investigate it more. And then it performs well both pre and post deepening, which is actually a worry that I had, is that, well, maybe this model doesn't have enough data of the post deepening to really be able to pick up on those trends. But it's shown promise in both cases. Okay, and then our final model, Model 2B, uses the same input data as before, but its output is just a prediction of do we need to dredge. There's no regression data, there's nothing of that case. It's just, do we need to dredge? So quick overview. We predict, do we need to dredge in 6 weeks? Yes or no? The testing scope for this uses all 4, 5, and 6 of the reaches of Southwest Pass, and the input data is CSAT-derived weekly average depths. So just like before, how far below? That was the same input data we used before. And it also uses DQM, which is dredging quality management, to know where were dredges historically. Will we want to put dredges there again in the future? Same desegregation as the model before. This uses a weekly scope and is also still under development. So DQM data collection. This contains information about where dredges were and their activities. What we want to do with this is we want to say, was there a dredge in Reach 4 during this week? If there was a dredge in week 4, we're going to put a check mark next to that and say, when you predict on this, try to predict a 1. Whereas if there wasn't a dredge, when you predict on this, try to predict a 0. So we're just associating dredge locations with maps of volumes. So data generation. This data was very, very imbalanced. There's about 20 no dredge events for every dredge event. So we went to what we call oversampling, where we take our original data set and we create many, many copies of it. So our original data set has about the same size as our other set, our set of don't dredge. We did this with some mirroring, some other things to kind of change it. So it's not just training on one image over and over again. And then hopefully also by doing mirroring of the reach, it makes the model a little bit more robust and able to predict on a wider range of features. So similar to before for our CNN construction, but instead of taking 8 weeks, it's only looking at one time 6 weeks ago. This input layer, it can work with all reach shapes within a specified range, compared to the previous model, which we had to give it very, very strict values for what can be put into here. And you can see here are an image of reach 4, reach 5, and reach 6. And even though they have different shapes, the model takes them and is able to predict on them all the same. As talked about in the last two models, when training the model, accurately predicting a dredge is much more important than accurately predicting no need to dredge. We did this with this in mind. We then weighted the dredge cases 2.5 times higher. It rewards the model when it makes a correct prediction than a prediction for no dredge. So while making a no dredge prediction is still, helping the model, showing that it's doing the right thing, predicting that it doesn't need to dredge, that it does need to dredge when it does actually need to dredge, much, much more rewarding, and it led to us being able to make stronger predictions. So here are our results. Sadly, with a model like this, with no real regression, there's not as many pretty figures. So I'll try to make this as interesting as I can. So the predictions from this model, you can see that the no dredge case, it got 52 out of 52 of these correct. Like every single time there was no need to dredge, got this right. When there was a need to dredge, it got 18 out of the 24 of these correct, even putting the weighting on. A weird thing happens if you weight too heavily. If you weight too heavily, it gets rewarded so much for predicting there's a need to dredge that it doesn't really care about getting this correct, and it just shifts every single value into yes, dredge now, dredge now. Kind of would make sense. You're rewarding it too much, it does what gets it the reward. And then down here, we can see our violin plot. And this is the actual value that it predicted. It's confidence that there's a need to dredge, is this prediction here. And the nice thing that I like about this, even though these 0.2s are not actually zeros when there's no need to dredge, that's probably an effect of the weighting that we did on the two classes. You do see two very, very distinct classes. If we were seeing a lot of predictions in this 0.5, 0.6 range, you're almost flipping a coin on. It's almost flipping a coin. Should I dredge? Should I not dredge? But with these values being at like 0.2 and up to about 1, when it makes a prediction, it's confident on that prediction, which is very nice because it means that feeding it new data, it should also still be confident on those future predictions. It also is why these 6 cases are probably going to be a little bit hard to figure out. We want to look into this. There might be some events that happened, right? It's looking 6 weeks into the future. If a storm happened, hurricane came through, well, it's not going to know that 6 weeks prior. These are 6 cases where no matter how much we weighted, how much we look at, changing the variables, it just doesn't have the data. So by adding more data or, adding these other models that we talked about earlier to also look at, it might be able to figure things like that out. Adding things like weather data is something that I'm interested in, but I'm trying to figure out how to add that accurately. For this model, though, we got an accuracy of 92%, a recall of 75%, and a precision of 100%. The precision variable is just saying it always knows when there's no need to dredge, which is still good. So in summary, this model's still in development, but it's predicting strongly. So the no information rate is something where you take the most probable outcome and you always predict that. The no information rate for this is 68%, which would just say never dredge. And our accuracy is at 91%, so much, much higher than this no information rate. That shows a strong model. And then having 2 different approaches, both using the CNN, are also nice because you can combine these models much more easily. Adding in the LSTM is going to take some work on that ensemble modeling, but adding 2 CNNs together is very strong. So by adding this with our previous results from the other CNN model, we should be able to find some good results out of that, some good future work. So to go over, we have 3 models. Model 1 was the LSTM, which is regression data that we then classify. Shoaling trends is what it is. Do we need, how much shoaling is happening right now? Model 2A is looking at the depth of the river over a span of 8 weeks and saying, well, what do we expect the depth of the river to be, 6 weeks from now? Is it going to be above our threshold of 20% being above our, is it going to be, is 20% going to be above our threshold, or is less than 20% going to be above our threshold? And then model 2B, it takes an image from 6 weeks ago, looks at it and says, well, historically 6 weeks from now a dredge would be here, so I'm going to say we should put a dredge out there. And hopefully we can combine all of these models together and get even better results. I'm going to hand it back over to Jerry. Thank you
Thank you,
all for
Jacob.
listening.
That was a great presentation. I have to admit that most of us don't think very much about harbors, navigable waterways, and ports. And I think it was most recently accentuated with the collapse of the Key Bridge in Baltimore. Before we get into the Q&A period, and we do have a number of questions that we'll speak about, I'd like to cover, as we normally do, some near-term upcoming webinars. For those of you who've been with us over the past 5.5+ years on these monthly webinars, you know where to register. You see it on slide number 49. On October the 30th, Dr. Ahmad Al-Hassan will be presenting contactless energy-based tire pavement traction models. That's a mouthful. So that's, again, a pavement-related topic. On November 20th, Merchant Callis will be presenting Army sustainment challenges and new approaches to addressing them. I'd like to remind our audience that all of our presenters are ARA employees, and we have a diversity of topics and business services that we provide. Many people think of us as a singular service company, but we're very diverse and very deep. So with that, I'd like to remind you also that we've got a number of topics planned through the first part of 2025. And just watch your email for updates and go to ara.com/webinars, and you'll find the latest information. Also, for those of you who have colleagues that missed today's program, you can see the recordings. All of our programs are recorded. So let's take a look in the time that's remaining at a few questions that we have. First question is from Dan. And Dan, Jacob, would like to know, what additional data would you like to have to improve your models?
So one thing, like I was saying at the end of the presentation, that I would very much like, weather data. There's events that happen in the Gulf of Mexico all the time, and we're trying to make predictions 6 weeks out. If something happens in that 6-week time span, we're not going to be able to train on that, be able to make predictions on that. So maybe it's not going to help with our predictions, but if we have poor predictions and we can correlate them to, well, there was a very, very big weather event. Well, of course, we're not going to predict that there's going to be a lot of shoaling happening then, because a hurricane, a storm, pushed a bunch of debris in the Mississippi River. Another thing I would like, I said that not all stations that we're getting data from have the same sensors. Turbidity is an amazing predictor for what's going to happen downriver with shoaling. We only have about 3 turbidity sensors in all of those 69 stations that we're getting data from. So more turbidity sensors would also be very great. I would very much like to be able to use those.
Thank you, Jacob. And we do have a limited amount of time. We'll go till about 3 minutes before the hour, before we wrap things up. Next question is from Twyla. Twyla would like to know, how do you plan to generalize these models to other rivers and waterways within the United States?
So right now, our final model, Model 2B, it seems very strong on generalizing. It was able to, we have initially just looked at reach 6, but we were able to move to reach 4, 5, and 6 very quickly. So hopefully a model like that can be generalized quickly. The LSTM would definitely be the hardest, because the data it's using is based off of upstream gauges. You go to somewhere in the Northeast, what's happening in St. Louis isn't really going to be important to them. So that would take a little bit more work, but we would find comparable sensors, comparable readings for things that had happened upriver. We'd probably have to train a new model, but the lessons we've learned building the LSTM that we already have would make that process so much quicker than going through it for the first time. Model 2 is a little bit similar. Model 2A is a little bit similar to the final one. It's a little bit more strict right now on what its input ranges can be. So that would probably take some fine tuning, but that's our hope, is that each model has a way to generalize. Generalizing each of them is probably going to take a different amount of work.
Okay, next question is from Joseph. And are there other variables that you'd like to investigate in relation to river navigability?
So another variable that we've looked at a little bit is something like precipitation. And while precipitation itself hasn't been an especially strong indicator, I think it'd be interesting to know if this precipitation is happening in an area that's uh, has a lot of loose soil, something that could easily fall into the river, get dissolved. That could be interesting because that's going to come out of solution at some point downstream, and that coming out of solution would lead to more dredging. Uh, there's some other variables that could definitely be interesting to look at. So you have salinity. It's similar to turbidity. We just don't have enough sensors for salinity to really get a good grasp on how valuable it would be. But a few tests with salinity has shown some strength with that. So getting more salinity data, just more dissolved solid data, is always variables that I would like to look at.
Okay, thank you. Next question is from Abu, and the question is, are there any other model types that you think would be applicable to this type of a problem?
There's one thing that I've been looking at for a little bit of time now. It's called an autoencoder. And what it does is we take something, model 2A, we take the map in, and we wouldn't try to generate a number on the output. We'd try to generate an entire map on the output just 6 weeks down the line. That model is used a good bit for things like cleaning up images. If you have, say, painting or something that has like a smudge on it, uh, that can clean it up to make it look new. It could also, if something's off center at an angle, it can also be used to generate an image. There's some examples of this almost being fed an image and then generating a stylized version of that image on the other side. So if we could figure out a way to make something like an autoencoder work for time series data or a regression problem, I think that could be very, very strong. Because instead of just having one point or one value, you'd have a good idea of what the entire bottom of the river looks like in one section 6 weeks down the line, or what we predict it to look like 6 weeks down the line.
Okay, we have another question from Sarah, and Sarah's question, I'll ad lib a bit here, is that this was a research study, as you pointed out, for ERDIC and the core.
Mhm.
Do you have any thoughts in terms of how it may be implemented by other divisions and offices of the core or put into mainstream practice? Any views
So
from your work?
the one that I think could probably be moved to the most places is our two-way model, the one that's using image data to make a prediction on a variable down the line. I've only seen that used in one or two other places, a lot of the time dealing with things like bacterial culture growth, predicting how much that's going to grow in a time period. But I think you have so many different avenues that you can use time series images to make a prediction, something like crack growth. So if you have, crack in concrete, crack in a bridge, something like that, where do we predict that crack to look like, out after a certain amount of time? You absolutely would need to collect a large amount of time series data for it to learn trends. But being able to make predictions not just on on raw numbers, but predictions using images themselves, I think has a wide range of avenues that it could go down.
Yeah, that was meaningful, but Sarah's question was really focused on the
Oh.
actual application of the results of the tool. Have you thought
So
at all about that with your clients?
so with this tool right now, um, we're leaning towards like a district implementation so that each district in the Army Corps is going to be able to make their own predictions on when they need to call in dredges. Um, right now, like I said, we're only really training on Southwest Pass, but we're hoping that by being able to give it out to all districts of the Army Corps to make predictions.
Okay, thank you. And we're running out of time. That was a great Q&A period. If we didn't get a chance to address the questions that you submitted, Jacob, like all of our presenters, has been gracious to entertain questions for the next day, 24 hours, on the topic that he presented today. You should see his email address. You do on slide 50. Please make sure that those questions are kind of a technical nature and not really requesting anything that's specific consulting. And we may, depending on the form of the question, may not be able to address the question based on the sensitivity of certain projects, such as this one. So all webinar participants, as usual, who have joined us for the entire hour of the program are entitled to receive a PDH certificate for 1 hour. They'll also receive a PDF copy of the presentation. Please allow us, this slide says 3 weeks, but we're got a few difficulties right now, administratively short on staff, so it may take up to 4 weeks. Please forgive us. Contact us at the address that you see here if you have any questions. Like everybody on the planet, but we're better than everybody on the planet, ARA is hiring. And our motto, you see, discover your passion, but I love our motto of science and engineering for fun and profit. If you're interested in employment opportunities with ARA Transportation and Infrastructure offices, please send a brief resume and your contact information to the address that you see here. I want to remind everybody, we're a company of about 2,300, 2,400 people, and we are a 100% employee-owned company. That's pretty unusual in today's environment. So I want to thank you all. God bless you all. Have a great day and a great week. Thank you again, Jacob.
Thank you.